Okay, so let's go back to the same problem, but this time we are going to use the virtual work method to solve the problem. Okay, so how does the virtual work method work? So virtual method is simply a work energy method wherein a virtual displacement is actually multiplied to the real force, okay, to create a virtual work. So this time, we assume that your deflection curve uh, will constitute a virtual displacement delta y, okay, which is of course here, it is linearly increasing from 0 to a maximum value. Okay, so what we are going to do now is to simply to multiply all the forces involved. So this is now your reaction in the system. The reaction. We also have here the spring. Okay, spring force. We also have here the reverse effective force or the inertia force, my double dot. And instead of using a representation of the inertia force in a triangular manner, let us use a different approach. Okay, so let us try to use the mass multiplied by the length of the rigid bar concentrated at the center of the rigid bar. So this is now your M, L, okay, and then we have here, of course, your uh, acceleration. So if this is a Y, at this point here, this must be Y over 2. Okay, so since the distance from here to the center is 1/2, so your displacement here is 1/2 of the displacement at the end. And so is true with your virtual displacement here. Okay, so this becomes delta y over 2. Okay, so this is now ml concentrated here multiplied by y double dot over 2. And of course, since this is rotating in a certain manner, so this will now constitute a rotational inertia equivalent to I times alpha. Okay, so we're going to solve now. Instead of having four forces, we ended up into 5 forces, including the mass moment of inertia of the system. Okay, so your equations now become, before we do that, we try to solve what is I of the rigid bar. Okay, so we try to take note that your I is simply the mass moment of inertia of your rigid bar. Okay, so the bar is a rigid bar. Okay, so this is now equivalent to simply in terms of your elementary mechanics, this is simply 1/12 of the mass times L times cube. Okay, so it's like BH cube over 12. This is ML cube over 12. Okay, and your alpha is simply the rotational acceleration, angular acceleration, which is of course based on the coordinate theta. So if I will solve the angle theta here, so theta is simply equal to y over L. Okay, so alpha now is simply equal to uh, theta double dot or y over L. Okay, double dot. Okay, so this is also equal to theta double dot. Okay, so substituting all the values using the virtual work approach, we simply multiply all the forces with the virtual displacement. So R times 0 plus K M L uh, Y double dot K over 2 multiplied by the virtual displacement delta Y over 2, okay, plus I alpha is 1 over 12 ml cubed times y double dot all over um, L, okay, and then you have to multiply this by delta, okay, so you have a delta theta, so since this is now a delta y, okay, so the angular the angular uh, virtual the virtual angular rotational displacement is now delta y over L. Okay, so this is delta y all over L. Okay, and then we have to add, of course, your uh, mass multiplied by y double dot multiplied by delta y plus your spring, which is ky multiplied by delta y. Okay, so everything is now multiplied by delta y. So we can simply cancel that off. Okay, so that's 0. So this whole here is 0. So what remains is 1, 2, 3 forces, 4 forces rather, and we can combine the 3 by simply factoring out y double dot. Okay, so this is now m l over 4 y double dot plus m this cancels. Okay, so what remains is 1 cancel, so this will ml over 12 y double dot plus capital M y double dot plus ky equals 0. Okay, so if we factor out, take the LCD of this, I think this becomes mly, that's 3 plus 1, 4 over 12 is 1/3. Okay, all over 3 plus my double dot plus ky equals 0. Factoring, we get ml over 3 plus capital M y double dot plus ky equals 0. So this is the same as that equation.